Let's talk about P series and harmonic series, and this is the easy one. We just have to know how to identify it, and we have strategically pointed at a couple of these with ink pens. So we want to determine the convergence or divergence of these series, but that actually happened in a previous lesson, in a previous video, when we found that this series diverges because its functional equivalent as an improper integral also diverged. So, surprise! You know what's about to happen, right? And then this one converged because its functional equivalent as an improper integral also converged. And surprise, there we go. So there is an understood number down here, and no one is surprised when I write the understood 1 right there, and it's great. And what it really means is I have 1 over 1 to the 1, and 1 over 2 to the 1, and 1 over 3 to the 1, and 1 over 4 to the 1, okay? This is 1 over 1 to the 2, 1 over 2 to the 2, 1 over 3 to the 2, hard to say. But basically, the exponent of the denominator is the issue here, is the thing that determines what we're dealing with, and it's called a P series. And P is the exponent of the thing that we're counting up by in the denominator. The structure of this is sometimes confused for geometric because we just start mixing things up. We look at the structure and we're like, well, that looks like this or that looks like that. No. It is a P series if we have n as the denominator and we are raising that denominator to a power, okay? So here we go. What we're going to do is determine if it converges or diverges. Well, we know that it diverges when the exponent is 1, and it's going to converge when the exponent is 2. So here's the rule, and I don't have time to go into the proof of this, and actually I don't know the proof of this, but anytime the exponent is between 0, not including 0, because that just won't work, 0 and 1, including 1, we have a divergent series. And if it is greater than 1, we have a convergent series. So let's just jump right in. Determine if the P series test for convergence can be used for each of the series below. Let's start there. Is this a P series? Is this the same structure as that? Yes. N is the denominator and it's raised to a power. So this is a yes. And then the next question is, what is P? They didn't ask that, but I need to know. So P is 3. Because P is 3, this series converges. I told you this was easy, right? All right, let's go to the next one. Is this a P series? No, it's not. Now, it looks like it a little bit, but keep in mind where your n is. Here, the n is the denominator raised to a power. Here is a number raised to the n power. That's different. It's a very different structure. This one actually is geometric. They didn't ask, but it's geometric. And I do want to determine if the series converges or diverges. And I think I can, because in this case, now that we're dealing with a geometric series, I could rewrite it if I wanted to, and I do want to rewrite it. So this is truly what I'm dealing with. I'm going to treat it like 1/3 to the n power. It's totally the same thing, right? Because I could raise 1 to the n power as much as I want. And that means that R, my common ratio, is 1/3. And because 1/3 is between -1 and 1, we have a series that converges, which is not spelled C-O-N-G. I could switch the G and the V. There we go. All right. Well, look, we have n to a power. That looks like a P series. Is it? Is it? No. No, totally not. So this is a no. And it's not because it's not a fraction. If it was 1 over n to the 3, like the first one was, then that, of course, would be a yes, it's a P series. And we can actually decide if this converges or diverges, and it has nothing to do with P series, of course, because it's a no. But I could look at that exponent and just realize I'm dealing with 1 to the 3rd plus 2 to the 3rd plus 3 to the 3rd. So we have 1 plus 8 plus 27 plus 64, and this is going to get really big really fast. So this one's just going to diverge all over the place. Diverge all over the place. Don't write that as a phrase, but there we go. Okay, now we get into some that are a little bit trickier, and we're going to try to rewrite these to look like that so we can determine if that is the structure indeed. So this is the sum from, we'll start at 1 to infinity, and this is what's really going on. I have, let's start with the second term. I have 2 cube root of 2, and then cube root of 3, and then cube root of 4. So it looks like whatever term I'm on, that's what I'm dealing with, and I'm cube rooting it. Well, cube rooting is the same as 1/3 power. So this is what I'm dealing with. And if you wanted to, you could say this is really the cube root of 1 in the denominator here. It's the same thing, right? You're dividing by 1, so that changes nothing. So we have 1 over n to the 1/3 power. Well, n to the 1/3 power, is this of this structure. I'm running out of space. Once I get to the bottom one, I want to be like, are they the same? But right now it's like that. So the n is the denominator, and it's raised to a power. And okay, so yes, this is a p-series. Yes, it's a p-series. Okay, let's decide what p is. P is the exponent. It's 1/3. And then I look at it and say, well, if p is a third, what happens? We have a divergent series. So if I listed all these terms and I added them all up all the way to infinity for the rest of eternity, which I'm not going to do, I have better things to do with my eternity, then I would find out that they diverge. There we go. Okay, number 5. I need to decide what this one is as well, so let's do this. Let's actually just call this 1/1 because it kind of helps to figure things out sometimes. So n equals, I'm reluctant to start at 1. I'm actually going to start this one at 0. How do you know? Well, you'll know when you get into it. I would like to think this one was fairly obvious because the second term had a 2, and the third term had a 3, and the fourth term had a 4. This one's not as obvious, and we will go to infinity on this. And there's definitely a fraction involved. I think we can go ahead and get that much structure already. So how do I know this one's is going to start at 0? Well, let's think about it. Let's think. Let's look at the numerator, actually. 2, 4, 8, all right? Clearly the next one's 16. This is 2, 4, 8. Let's think of powers of 2. That's 2 to the 1. That's 2 to the 2. That's 2 to the 3. Next is 2 to the 4, but that's the 5th term. Okay, so 2 to the 1 is technically the second term, so this must be the 0th term. This must be, first term, 2 to the 0 power, so 2 to the n power, 2 to the 0 in this case would give me 1. So I have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So we're starting with 0. Let's deal with the denominator. This is 5 to the 1. This is 5 to the 2. This is 5 to the 3. So this is 5 to the n. This is 5 to the 0. Okay, this is what we have. Let's rewrite it one more time because I would like to think something's fairly obvious. We have 2 to the n over 5 to the n. We really have 2 over 5 to the n. And therefore, this little guy right here, is it a p-series? No, the exponent is an n, so this is going to be geometric. So no, it's going to be geometric, and we can go a little further. Does it converge or diverge? And well, let's find out. Let's find out. So we have an R value of 2/5, and because 2/5 is, you don't have to write this every time, but I'm just over-explaining, is between -1 and 1, then we have a series that converges. There, that's how you spell it. All right, let's move to the next one. And I would like to write this one as a series as well. And I need to figure out where this one starts. Does it start at 0? Does it start at 1? Does it start somewhere other than that? It's possible. It's kind of rare, but it could. Let's just go ahead and go with the fact that the denominator of the second term is 2 and the denominator of the third term is 3. So this one does start with 1. So 1, 2, 3, 4. And we have, let's see. That's n right there. I'm going to a little bit of over-explanation on this one. This is n down here, and the numerator is n, but it's cube-rooted, so this is n to the 1/3 power. There we go. That's what it is. Now, you look at this and you say, is that a p-series? Look at this. Compare it to that. Are they the same? No, they're not. Hold that. Hold that thought. They're about to be. Watch this. If I have, I'm making this up. You've seen this a million times, and ignore the doodling. Here, let's use this. That's x to the 7. If I had x squared over x to the 7, I'd really have x to the 5 in the denominator, right? Right? Right. If I have n to the 1/3 and I have n to the 1, I can subtract my exponents and do 1 minus 1/3, get 2/3. Ah, see? Yep. Yeah. into the 2/3. Okay, is this a P series? Yes. Was this a P series? Yeah, it was just harder to identify. So this is a P series, so yes, it's P series. Therefore, I need to identify what P is. P is 2/3, that's the exponent. P is the power, that's what it stands for, in case you needed to know. So 2/3 is between 0 and 1, therefore this series is going to diverge. All right, last one. Last one. Let's write the general structure of this little guy right here. Da-da-da-do-do. N equals, let's just start with 1. So 1. Let's call it 1 to the E because you can see the pattern, and 1 to the E is 1, right? So first term has a denominator of 1, second term has a denominator of 2, third term has a denominator of 3 to the E. So we are really dealing with a fraction that has a consistent 1 in the numerator and whatever we're counting by in the denominator, and it's raised to the E power. Is this a P series? Yes. What you're counting by is the denominator, and you're raising it to a number. E is a number, you know that, you're in calculus. So yes, this is a P series, and P equals E. So because my power is E, which is 2.7 and some decimals, that is greater than 1, the series is going to converge. So it converges. Okay, notice that I never told you what any of these converge to. The geometric ones, could have found it. Totally could have been like, yeah, let's crank that out, pull out a formula, do it. But we don't know what the series actually converge to in a lot of cases. Again, there is an exception. This one is pi squared over 6 because someone found it out years ago. It's amazing. It's beautiful. But what's this one? No one knows. Actually, I had a college professor one time. Here I am at the end of the video, just rambling. He said, if you can find out what this converges to, you get an instant doctorate. And people have the decimal for it. Like you can get the decimal up to, probably millions of decimal places, but they don't know what it is. Like this one is so beautiful because it truly converges to be pi squared over 6. Like where does pi squared come from in the 6? And in case you care, and this is lovely, there's a pattern for all of them that are even. This is pi squared. I want to say it's 48. I need to stop before I go further and mess up further. But they know the even ones, they don't know the odd ones. Of course, they know the first odd one diverges. So notice the title, back on track. P series and the harmonic series. What's harmonic? We haven't even talked about that, and the lesson's over because there's not a backside to this one, right? So this right here, 1 over n, is called the harmonic series, and you are going to encounter that a lot. It is harmonic for truly musical reasons, actually, because you can split a length up into integer fractions. Into integer fractions that are based on a denominator that's an integer, and you can get some harmonies out of it. It's harmonic. It's amazing. The connections. It's lovely.